This video covers capacitance and capacitors. First, we need to talk about a capacitor. A capacitor consists of two plates with opposite charge. A capacitor is used to store charge and energy. The capacitance is going to be labeled with a C. It's the capacity of a capacitor to store charge. So capacitance is going to have units of farads, which will be represented by an F. So everything in parentheses is a unit. K is going to be the dielectric constant. It's the insulator between the plates, and we'll talk about that in the next slide. E naught, we've seen this value before. It's the permittivity of free space. It's equal to 1 over 4 pi times K, which is 9 times 10 to the 9th. A is the area of one plate. Again, this is going to be a meter squared. And D is the distance between the two plates. Again, a unit of length, so in meters. Again, a dielectric constant is an insulator placed in between a capacitor. So here we have a picture of a capacitor, which again is just two plates. Each of them has the same charge, Q. And over here we have a capacitor with a dielectric in between. Again, a dielectric is just a constant, and this constant is going to have a value of K. Now, when we first started talking about capacitors, we're going to talk about the dielectric constant K is equal to 1. This is true for a vacuum, meaning no air. But when there is air, it's still very, very close to K is equal to 1. So we're going to assume that it's equal to 1 in both situations. So if a problem does not mention a dielectric, you're going to assume that K is equal to 1. Again, what this dielectric does, it prevents charges from moving between the plates of the capacitors and are constructed with an insulator between the plate. Now this part is very important. We can talk about increasing the capacitance, but this all has to happen before the capacitor is created. Remember that capacitance is set at the factory. So these changes can only happen before the capacitor has been created. So if you want to increase the capacitance, you would have to either increase K. This is done by using a stronger insulator. Increase A, again, just increasing the area of the plates. Or you can decrease D, meaning you can put the plates closer together. So once a capacitor is manufactured, the capacitance C becomes a constant. So the amount of charge stored on it will depend on the voltage added to it instead. If we know the capacitance, then we can solve for the charge stored on the capacitor. Now we can use the equation C is equal to Q over V, where C is a capacitance. Again, this is units of farads. Q is the charge stored on the plate. Again, units of coulombs. And V is voltage across the capacitor, units of volts. So again, most of the time you're going to be asked to solve for the charge in the capacitor. So it's convenient to rearrange this equation and memorize it as Q equals C times V. The other very important part is that the charge stored on the plates is opposite and equal. So we mentioned earlier that if we have these two plates and you have a charge of 2 coulombs, what that means is that one plate will have a positive 2 coulomb charge and the other plate will have a negative 2 coulomb charge. Again, you wouldn't say that it has 4 coulombs, it simply has a charge of 2 coulombs. So when we start talking about charges on capacitors, then we can start talking about the energy stored on a capacitor. To solve for the energy stored, we know that energy is represented by a U. So we have U is equal to 1/2 Q times V, which is also equal to 1/2 C times V squared. Again, these two variations just come from using the equation Q equals C times V. So you can either just memorize one and derive the other, or vice versa. Again, U is going to be energy in joules, C is capacitance in farads, Q is charge in coulombs, and V is voltage in volts. Now, the very important part is that you do not confuse this with potential electrical energy. this is not the equation, and these are not equivalent to each other. Again, this is the energy on a capacitor. This was the energy of a charge in a potential. Now, you don't have to write this down because it's a lot of information. I just want you to know where that 1/2 comes from and how we're actually charging this capacitor. Now, you're going to start with an uncharged capacitor, and we'll see a simulation of this in class, where our charge is equal to 0, and our potential across the capacitor is also equal to 0. Now, we can connect this capacitor to a 6-volt battery. This volt battery is going to provide the electrical pressure. It's going to make my charges move. Again, this pressure removes negative charge from the left plate, sending it around to the right plate. That means that the left plate is going to lose electrons and become positive, and the right plate will gain electrons and become negative. This was done easily since there was no charge on the capacitor and had no pressure of its own to stop the charges from piling up on it. Now that it has a charge, it also has voltage and generates a pressure opposite the battery. Since it only has one charge, the voltage and pressure are small, and the larger pressure of the battery wins. However, as more charge is added, the voltage of the capacitor grows, making it more and more difficult to add charge. Now, this part you should write, that the charging of the capacitor stops when the forward pressure of the battery equals the backward pressure of the capacitor. What that means is when the capacitor is fully charged, meaning the voltage across the capacitor is equal to the voltage applied to it by the battery. That's when it stops charging. Now you can see from this graph that the relationship between charge and voltage is linear, but it's a triangle. So if we want to solve for the area under it, we'd have to use 1/2 Q times V, which gives us energy. Again, this tells you where that 1/2 is coming from. So let's try this example. We have a capacitor that has a plate of area 1.0 times 10 to the negative 4, and the plates are 0.2 millimeters apart. Again, to make sure that we have that in a number that's useful, we have to move our decimal 3 places to the left, and that becomes 0.0002 meters, or 2 times 10 to the negative 4 meters. And we're asked to determine its capacitance. Again, a dielectric was not mentioned, so we're going to assume that this has either vacuum or air in between it. So, to solve for the capacitance, remember it is K epsilon naught A over D. Again, our capacitance is equal to 1, and our epsilon naught is 1 over 4 pi times K. Our area was 1 times 10 to the negative 4. And the distance between these two plates was 2 times 10 to the negative 4. Put on that in your calculator, and you get 4.4 times 10 to the negative 12. Now, since we are solving for capacitance, that's in units of farads. Or you could also rewrite this as 4.4 picofarads, which is 10 to the negative 12. Now, this capacitor is connected to a 6-volt battery, and we want to determine the charge stored on it when it is fully charged. When it's fully charged, that means that the voltage across the capacitor will be equal to 6 volts. So, Q is equal to C times V, or 4.4 times 10 to the negative 12 times 6. You should get 2.65 times 10 to the negative 11. Again, we're solving for Q, which is in units of coulombs. Or you can even write this as 26.5 picocoulombs. coulombs. And the last one, we're asked to determine the energy stored when it is fully charged. Again, fully charged means that the voltage across is equal to the voltage of the battery. So our energy is going to be equal to 1/2 Q times V. We now have Q. Now remember, you could have also used the other equation for energy, but that one has a squared in it, and that's the one I tend to forget myself. So you can either derive it or you can just use the information we now have. Which gives you 7.96 times 10 to the negative 11. Because we're solving for energy, this is in unit of joules. Now again, these are the types of problems that you're more likely to see on the multiple choice section of the AP exam. Here, the only way that you can change charge is by changing the voltage, because capacitance at this point is a constant. So, if the capacitance is a constant, then if you double the voltage, then you double the charge. Again, if you double the charge and you double the voltage, then you are multiplying our energy by a factor of 4. Again, the only way the voltage could have increased like this is if we have a power source that has a varying voltage. You cannot do this with a battery because batteries have a set voltage. Here, we're going to talk about when the voltage is constant. Now, in this situation, we're dealing with an adjustable capacitor, and the space between this adjustable capacitor is doubled. So, if the space is doubled, then the capacitance is halved. Again, here we're told that our voltage is constant. In the situation where we have a battery would have a constant voltage. So, if we have a constant voltage and my capacitance is halved, then my charge on that capacitor is halved as well. If you half the charge and my voltage stays constant, then you're going to halve the energy on that capacitor. In the last situation, let's say that we have a capacitor that is fully charged by a battery, and the battery is removed. Again, what this meant is if we put a battery and we allow this capacitor to charge, the charge that it has is going to be the same on both plates. So let's say it does all of that. Now what we can do is the charge is going to stay the same, but let's say that we now increase the distance in between the capacitor. So what that means is you're halving the capacitance. If that happens, then that means we have to double our voltage in order for the charge not to change. Now, while the voltage of a battery is assumed constant, the voltage of a capacitor is subject to change. Again, if our charge did not change and we had a decrease in our capacitance, we had to have an increase in our voltage across our two plates. Again, if all of those changes happen, then our energy will double. Again, you don't have to write this part down. You really should only be focusing on anything that's in any text that's in color. So don't write. I'm just going to talk about what happens inside of a battery and how we use that to calculate our voltage and our resistance in a circuit. So, batteries consist of plates that are charged by a chemical reaction taking place between the plates. The reaction provides the energy to lift charges from a low potential to a high potential. And the EMF, this is the part that we're going to focus on, created by the chemical reaction is a potential difference that drives the electrical devices attached to the battery. Like other sources of power, batteries are not 100% efficient. Since batteries are made of conducting material, they have resistance. And the resistance inside of a battery is called the internal resistance. This part you do need to write. The EMF of the battery is a theoretical potential that would have been reached if there were no resistance. The actual potential produced by a battery is less than the EMF due to the loss created by the internal resistance. The actual potential is called the terminal voltage. Now, again, everything in color is important. The terminal voltage is the potential difference between the terminals or the ends of a battery. This terminal voltage, which is V, is equal to the EMF produced by the battery minus the current in the battery times the internal resistance, lowercase r. Now, for the most part, when we have our internal resistance is negligible, which is the case in most problems, then our voltage will simply be equal to the voltage stated on the battery, or also known as EMF. Now here we have a graph of terminal voltage. The equation for terminal voltage is linear, as we can see in this equation. To determine the exact look of the graph, simply rearrange the equation to match the y equals mx plus b equation that you're more used to. So if you're asked to solve for the voltage versus current graph of a battery, again, anything versus anything means y versus x. So that means current is going to be on the x-axis. Again, we rearrange this equation so that it matches the mx plus b. And so we can see that our slope is going to be our negative r. I is on the x-axis. V is on the, what we see here, the graph, the y. And our EMF is our y-intercept. So again, this problem is pretty straightforward. A battery has an EMF of 6 volts. Again, that EMF is our little sigma symbol here. And an internal resistance of 0.10 ohms. Remember that ohms is a unit for resistance. And we're asked to determine the terminal voltage, which is V, if we have a current of 3 amps running through the battery. So we're given all of our information. We can simply plug it in, and we get a terminal voltage of 5.7 volts. Again, for the most part, internal resistance is going to be considered negligible unless you're otherwise told to include it into your equation. So when internal resistance is negligible, R is equal to 0. That means this piece is going to go away, and all you're left with is our terminal voltage will be equal to the EMF produced by the battery. So when working with batteries, Ohm's law and the power equations modify as follows. Again, you really don't have to make these modifications unless you already understand what's going on, but it's a good idea because you might see them in this form on your multiple choice questions. And lastly, we're going to start getting into the real circuits building problems next video. So it's important to already be familiar with the symbols that we're going to be seeing. So make sure that you copy all these down, and we'll go over them next time. Again, this is an ammeter, and this is a voltmeter.